Welcome to this explainer. So, if you ask the average person on the street what 5G actually is, they'll almost certainly tell you it just means, faster internet for your phone. But let me stop you right there. If you write that down on a distributed systems or IoT final exam, you are absolutely going to fail. 5G is not just a speed upgrade. It's a complete structural overhaul of telecom architecture. For the literal first time ever, a telecommunications network was designed from the ground up to natively support massive IoT ecosystems and edge computing. Today, we're going to break down the heavy hardware and software concepts you need to truly master this architecture. So grab a notebook, because this is a heavy one. Let's dive right in.
Okay, here's our roadmap. First, we'll look beyond that faster internet myth, then break down the ETSI MEC architecture, solve the bandwidth crisis, explore the 5G service triangle, and finally, wrap up with the ultimate cheat sheet. Let's get to it.
Section 1. Beyond faster internet. We're kicking things off with a complete paradigm shift regarding what 5G actually does.
Just look at the stark contrast here between public perception and engineering reality. The myth that 5G is just about downloading movies faster on your smartphone, yeah, it's completely inadequate. The reality is that instead of just phones, 5G is built to handle thousands of drones, factory robots, and self-driving cars all connecting simultaneously. It's this massive structural overhaul designed explicitly for massive IoT and native edge computing. So do yourself a favor and erase that myth from your mind right now.
Moving into Section 2, the ETSI MEC architecture. To understand how 5G handles all these devices, we really have to look at the new brains located right at the cell tower.
Which brings us to MEC. Multi-Access Edge Computing is a standard defined by ETSI. That's the European Telecommunications Standards Institute. Its entire goal is to provide cloud computing capabilities and an IT service environment right there at the edge of the network. Now, I really want you to pay close attention to the word multi-access here. It's actually not called mobile edge computing anymore, because this architecture intelligently supports 5G, Wi-Fi, and fixed-line networks all at the exact same time. Pretty cool, right?
So if you ever need to explain MEC architecture, these are the three absolute must-know components. Let's assemble this mentally, starting from the top down. Number 1 is the MEO, the Mobile Edge Orchestrator. Think of the MEO as the top-level boss. It maintains a global view of the entire network. Now, why does that matter? Well, imagine a self-driving car moving from city A to city B. The MEO is the boss that actually decides to migrate that car's edge computing applications over to a new server that's physically closer to the car's new location. It oversees the whole shebang.
Stepping down a level, we've got the MEP or MEC platform. This is your execution environment. It's where your local IoT applications are actually running. But, it does a lot more than just run code. It provides essential services like radio network information. Because the MEP can see real-time cell tower congestion data, the applications running on it can actually adjust their own data rates automatically, so they function as efficiently as possible.
And then there's the UPF, the user plane function. This is where the real magic of 5G integration happens. In older 4G networks, all that data had to travel all the way back to a central core network before it could even hit the internet or an application. The UPF totally changes the game by acting like a localized traffic cop. If the UPF sees a data packet intended for a local edge application, boom, it routes it directly into the MEP. It completely bypasses the need to send data halfway across the country to some massive cloud data center.
Section 3. Solving the bandwidth crisis. So we've got the physical edge hardware in place. But zooming out slightly, we run into a massive software problem when this physical hardware is forced to handle everything at once.
Just imagine you have a single 5G cell tower serving a really busy city block. Connected to this exact same tower, you have a hospital running a remote robotic surgery, a factory running automated assembly lines, and, let's say, 10,000 teenagers all streaming 4K video. If those teenagers suddenly overload the tower and that remote surgery lags, well, that's a literal crisis. In a traditional network, all of this traffic fights for the exact same pool of resources. And honestly, that's completely, unequivocally unacceptable for mission-critical IoT devices.
Which leaves us with an incredibly urgent question. How do we guarantee that those mission-critical IoT devices, like a robotic surgical arm freezing mid-operation, never have to compete for bandwidth with everyday consumer smartphones? Seriously, take a second and think about how you would actually solve that routing problem.
Well, the ultimate fix to this crisis is network slicing. Network slicing takes that one shared, massive physical 5G infrastructure, think of it like a giant fiber optic pipe, and logically divides it into multiple, completely isolated virtual networks. Imagine that main pipe magically sliced horizontally into smaller, distinct, glowing virtual pipes. Each of these slices is perfectly customized to meet a specific service level agreement, or SLA.
And to ensure complete isolation, 5G orchestrators rely on strict mathematics. Notice the formula we're looking at. The total network capacity absolutely must be greater than or equal to the sum of all guaranteed slices, plus the orchestration overhead. Because these slices are mathematically and logically sandboxed, a massive spike in data usage on the consumer video slice literally cannot steal bandwidth or processing power away from the hospital surgery slice. It's a real game changer.
Section 4, the 5G service triangle. So we know we can slice the network, right? But how do we decide what those slices actually look like? Let's look at the 3 distinct service classes defined by 3GPP that dictate exactly how these slices get configured.
When you're configuring slices, you absolutely must know the 5G service triangle. The very first pillar is URLLC. That's ultra-reliable, low-latency communication. Now, the crucial point here is that this slice completely ignores massive data volume. It really doesn't care about large files at all. Instead, it prioritizes instant, guaranteed reaction times. We're talking guaranteed latency of less than 1 millisecond and 99.999% network uptime. This is the slice you're going to use for autonomous vehicles, industrial factory automation, and yes, that remote robotic surgery we talked about.
The second pillar of the triangle is MMTC, or Massive Machine Type Communication. Actually, scratch that need for speed because this slice doesn't care about high speed at all. It cares purely about scale and efficiency. It's designed to support extreme density. We're talking up to 1 million connected devices per square kilometer. These devices are transmitting tiny payloads, maybe just 10 bytes once an hour, which allows sensor batteries to last for like 10 years. You'd use the MMTC slice for things like smart agriculture soil sensors, smart city water meters, or logistics fleet tracking.
And the final pillar is EMBB, Enhanced Mobile Broadband. This is your heavy lifter. EMBB is designed exclusively to maximize throughput and peak data rates for bandwidth-heavy applications, scaling way past 10 gigabits per second. So if you need to support augmented reality maintenance headsets, massive 4K security camera surveillance grids, or immersive VR gaming, yep, you allocate an EMBB slice. Section 5, the ultimate cheat sheet. We've covered the architectural hardware of MEC and the slicing software concepts of the 5G triangle, so let's bring it all together for a highly practical synthesis.
This matrix pulls absolutely everything we've covered together. Honestly, I highly recommend just taking a screenshot of this ultimate cheat sheet right now. You can clearly see URLC focusing on extreme reliability and low latency for things like surgery and cars. Then you see MMTC prioritizing high connection density and low energy for smart cities and agriculture. And finally, you've got EMBB driving maximum data throughput for your AR, VR, and 4K video streams. Everything in its right place.
So, to wrap this all up, 5G really is the ultimate enabler for fog and edge computing. By utilizing the ETSI MEC architecture, we move processing completely out of the centralized cloud and push it right to the cell tower using that localized UPF traffic cop. And by using network slicing, we guarantee that mission-critical IoT devices never have to compete for bandwidth with those teenagers on their smartphones. But you know, this leaves us with a pretty fascinating thought. Now that all this 5G edge processing and network slicing is up and running, how do these edge nodes actually filter, manage, and analyze this massive, chaotic stream of data before it ever even touches the cloud? Well, that's exactly what we're going to be covering in our next explainer on data management in the fog. Thanks so much for joining me, keep on learning, and I'll see you in the next explainer.